OK, so we have restored swiveling today. Let's see, is it moving? Yes, OK. So there was an email suggestion to do more on the pigeonhole principle, which I think is a wonderful topic. What do you think we might use in the midst of a pigeonhole principle argument? Yeah, maybe. We'll find out. OK, so it's Dirichlet's box or pigeonhole principle. I believe I mentioned this briefly in class before, but imagine you have n+1 pigeons and you have a pigeon gun. Okay? These are acceptable. You can bring a pigeon gun to school. You load the pigeon gun with the pigeons, and you shoot the pigeons into boxes. Okay? No pigeons will be harmed. These boxes are nice and cushioned. Okay? What can you say? So we have n+1 pigeons. I'm going to try. Pigeons. And we have n boxes. And we shoot the n+1 pigeons into the boxes. What must happen? One box has two pigeons.
One pigeon doesn't get a box.
Every pigeon goes into a box.
Okay, so one box has.
So one box, yes.
Or more specifically, one box has at least one box has at least two pigeons.
At least one. That's probably now what you said was correct. One box has two pigeons. At least one box has at least two pigeons. So at least one box has at least two pigeons. Have you heard the joke about the mathematician, the physicist, and the engineer traveling in the Scottish countryside? So they're traveling and they see a sheep, and it's a black sheep. And the engineer goes, aha, Scottish sheep are black. And the physicist goes, no, all we can conclude is that this Scottish sheep is black. And the mathematician goes, no, all we can conclude is there exists at least one sheep in Scotland which is black on at least one side. So you've got to be very careful. You've got to be very careful when you do these arguments not to conclude more than you're justified in concluding. So here for the pigeonhole principle, we have n+1 objects. We have n colors, color 1, color 2, color n. Each pigeon, if you want, gets colored with a different thing. It's the box it's going into. And the claim is that at least two of them must be colored the same. Maybe more than, maybe everyone goes into box 1. Maybe it's the place to be, right? Or maybe half go in box 1, half go in box 2. Maybe there's several boxes where you have at least two. But we're guaranteed there must be at least one box with two. Why? Well, if each box has at most one, I have n numbers to add. Each number is at most 1. The largest the sum can be is n. It cannot account for n+1. How many pigeons do I need before I'm guaranteed a box has at least 3 pigeons? 2n+1. Because if I have 2n+1 pigeons and I have n boxes, the average numbers of pigeons per box, this is a very important quantity, the pigeon per box average is just a shade over 2. If it's just a shade over 2, then one box has to be at the average or higher. If everybody is below average, that's ridiculous, right? If everybody's below average, how could the average be that? All right, so there's lots of different pigeonhole problems you can do. So I'm going to throw up a couple of them right now. Obviously, what do you think will be useful in solving these? Pigeonhole principle. So let's see. The first one, OK. Example. So let's let S be the set 1, 2, and I think, do I want to go up to 2n? Sure. 2n. The cardinality of S is greater than or equal to n+1. Prove there exists A and B in S such that A divides B. How many of you have seen this problem before? This is a somewhat famous pigeonhole problem. OK, good. Nobody is at least jumping up and immediately saying, I've seen this before. So when you're doing a pigeonhole problem, there's two things you need to identify. What are the two things we need to identify? Yes?
about a subset cardinality at least?
Oh, sorry. Sorry, yes. S is contained, thank you. S is contained in the set 1, 2, all the way up to 2n, and S has at least n plus 1 elements. And we want to prove that there are two elements in S where one divides the other. So when you're doing pigeonhole problems, you have to identify two things. What are the two things you need to identify?
Number of pigeons, number of boxes.
Close. Yes.
What are the pigeons?
What are the pigeons? What are the boxes? So you're very close. I agree it was implicit. That's why I said close. I didn't say you're way off. I didn't say you're crazy, right? What? I'm sorry? I know, but it would take too long to prove that in class. So what are the pigeons? What, and this is actually being recorded, oh well, what are the boxes? So that's the most important thing. When you're trying to determine what are the pigeons and what are the boxes, there's something that must be true at the end of the day. What must be true if you're going to do a successful use of the pigeonhole principle? Yes? There must be more pigeons than boxes, right? So when you're trying to identify what is the pigeon, what is the box, if at the end of the day you have more boxes than pigeons, try again. Okay? So what do you think the pigeons are? Yes? Allie is the pigeon, okay. What are the pigeons? So when you look at this, what do you think the pigeons are?
X.
The elements of S. Elements of S. Now, I have deliberately rephrased this problem from how it's normally done. I've said that S has at least n plus 1 elements. How many elements does S have? Yes? What if it had more elements?
Then it's like clear.
If we can do it in the case when S has exactly n plus 1 elements, could we do it if S has more elements? Yes. So in a problem like this, you might as well assume S has exactly n elements. I'm sorry, exactly n plus 1 elements. That's going to be the hardest case. What's the easiest case? S has 2n elements, okay? I'm not going to give you something like that. So let's make it a little bit harder. Now, it should not be immediately clear what the boxes are. So if you haven't seen this problem before, it's not clear what the boxes are. So the question is, how do you identify the boxes? Well, one thing to do is, whenever you're given a math problem, especially a puzzle, you always want to look at the numbers in the problem. These numbers are frequently chosen very carefully. We have teams of researchers carefully checking every possible case to make sure that there's maximum enjoyment possible and it's just barely going to work. What number do you think I could tweak a little bit and cause a catastrophe to happen? 2n. So I could make it n plus 1. So which do you think I should change, the 2n or the n plus 1? In some sense, they're equivalent. If I increase the 2n, that's essentially the same as making this smaller relative to that. Which would you rather do? Would you rather increase the 2n or would you rather decrease the n plus 1? Okay, let's decrease the n plus 1. So imagine the cardinality of t is equal to n. T stands for trouble. Next letter after S. This will be the troublesome set. Can you find a set of n elements such that no element divides any other? I'm sorry? So there's not enough primes, unfortunately, if n is large.
n plus 1 to 2n.
Ah, so maybe take t equal n plus 1, n plus 2, 2n. That works. Excellent. So we know that if our set has n elements or fewer, that it is possible that we may not have a divide b. The reason I'm doing this is I don't know about you, but when I first looked at this problem, I did not immediately see what the boxes were. So what I thought is, let me play with some sets. Let me build some intuition. The more you play, the more problems you do, the more things you explore, the better chance you have of seeing the connection.